Next up, we have Lauren Aldoroty from Duke University, and they will be talking about initial photometric results from the Roman DESC time domain survey simulations.
Hear me? Cool. Hi, I'm Lauren. I'm going to talk to you about validating injected type 1a supernovae in the Roman Open Universe time domain survey simulations. So what can we expect from Roman, first of all? Type 1a supernovae are extremely powerful tools for measuring the expansion of the universe, and Roman was designed with this in mind, and will conduct the high latitude time domain survey, which will be designed to leverage this. We expect to find more type 1a supernovae than ever, out to a higher redshift than ever, at better precision than ever, and there will be so many that the statistical uncertainty will be negligible, and statistics will be dominated by the intrinsic variation in type 1a supernovae. So in order to make this all worth it, we need to have some goals. Goal setting in advance, we love that. So in particular, Roman will be great for measuring the W parameters, and that's because we'll be measuring we'll be getting supernovae out to a higher redshift than before. And the way we start is you base your requirements on this value called the figure of merit, which is related to the errors in your W parameters. And you work backwards to figure out how to obtain the accuracy that you set out for, which is where the open universe simulations come in. As you stack experimental error contributions, the figure of merit decreases, and the error budget can be distributed accordingly amongst requirements like cadence and depth, number of supernovae, et cetera, redshift bins maybe. And then you can simulate observations and build a projected Hubble diagram to the specifications determined from that figure of merit. So I'm a member of the Roman Supernova Project infrastructure team. Our end goal is to build a Pixel 2 cosmology pipeline. In other words, we aim to deliver software that'll take us from raw Roman data to cosmological parameters with the accuracy specified. That'll include both catalog and image level simulations. The catalog level simulations can, help with designing things like observing strategy, but there are things that we can only learn from the image level simulations, like detector noise, artifacts, et cetera, that will then feed into the catalog simulations. So we'll have 3 simulation products. First is these catalog level light curves and spectra for all transients, not just type 1As. The pixel level high latitude time domain survey images with injected point sources from S and ANA, and those are the open universe sims, and this is the product that I'm talking about today, and 3D spectral data cubes. And eventually we'll be able to download and process these images in real time, which I'm really jazzed about because I think it'll be kind of fun. And in order to do all this, we need a difference imaging and photometry pipeline. That difference imaging pipeline needs to have some special requirements. It has to be precise, because supernovae will have a really large range of brightness across a large redshift range. And photometric systematics will very strongly affect constraints on the cosmological parameters. And in particular, there's a challenge that comes with Roman having such a wide field of view. It's got a spatially varying PSF, so how do we account for that? And it should also be fast. The pipeline should detect supernovae as soon as possible. They're transients, they don't last forever. We want to catch them as soon as possible. We've chosen to test this method called the Saccadic fast Fourier transform difference imaging method, or SFFT. It it has more accurate results than hot pants and is faster than both hot pants and Zogi. And in particular, it also accommodates the spatially varying PSF. So these two plots both show accuracy of SFFT. The y-axis in both plots is magnitude, and the x-axis, not the y-axis, is magnitude. And the y-axis on the left side is what this paper called the clean subtraction rate. The y-axis on the right side is RMS. And in both plots, you can see that the SFFT line, which is black and yellow on the left and right, respectively, performs better than hot pants. This plot shows the computation time. The x-axis is image axis length, so the size of your image, and the y-axis is time in seconds. And SFFT is the red line. It is a whole order of magnitude faster than the other three tested methods. So check boxes all around. It's precise. It results in fewer artifacts and has better accuracy than other methods, and it accommodates the spatially varying PSF. It's also fast. The computation time is an order of magnitude faster than other methods, and it's already been tested on transient data from ZTF, TESS, DCAM, and JWST. So it is a good candidate. These are what some of our subtractions look like. We're going to watch this twice, so just pick one and you'll get to watch the other one in the next go through. The one on the left is unsubtracted, and the one on the right is subtracted. So there should be a supernova appearing right now. Neat. And you can also see the second peak in the H-band, which is kind of cool. So second run through now. I'm going to stand here awkwardly and quietly while we watch. Cool, now you've seen both without, worrying about flipping your eyeballs back and forth between two of them frantically and then ending up missing everything. So those GIFs turn into these light curves, and this is the same supernova as we just watched. We successfully recovered the input light curves, which are the solid lines, with PSF photometry which is the circles, on the SFFT subtracted open universe Roman images, to pretty good accuracy as well. I will note that you may be wondering about the tails on the dimmer end. That's because these are still with a single epoch template for subtraction, and we did test different templates, and we found that it's the results are very, very sensitive to what template you use. So, when we get to co-added templates, that will go away. This is all coming with software. As everything that the PIT will do, there will be publicly available software associated with it. Feel free to check it out. It's very in progress, so I don't know that I would recommend using it right now, but there's some useful tools. It does aperture photometry, PSF photometry, SFFT difference imaging, and provides some tools for quickly accessing info and working with the open universe SIM files, which is probably the most useful part right now. So what's next? In the short term, like I said, immediate goal is to have co-added template images for subtraction to get rid of that upturning tail. Then after that, it'll be pretty quick to run this on a ton of transients and characterize transient detection efficiency versus signal to noise ratio for input to the catalog SIMs. And all of that will be written up in a paper. And then long term, we're going to build a full difference imaging pipeline to recover the input light curves from the open universe simulations, including object detection. In other words, not relying on the known coordinates baked into the SIMs, which currently I'm doing. Yes, it's cheating, but we got to start somewhere, and Rapid is doing that anyway. And then after that, develop a Pippin and SNANA job to get cosmological results, including systematics, from these recovered light curves. And that is my talk, and I will take questions. Thank you.
Any questions from the audience?
Oh no.
So, correct me if I'm wrong, but I believe the SFFT algorithm doesn't do fewer computations than the others. The real reason it's faster is because the code itself is written to run on GPUs. Isn't that the case? Or does it actually do fewer computations than the others?
That is partially true. It is written to run on a GPU, which makes it much faster, but it's also the standard difference imaging formula, but in Fourier space.
And
So
so
that
if
makes
you
it
run
faster.
it on CPUs, is it still faster than the others?
It is not, but that particular operation is fast on a GPU.
Yeah, okay.
Yeah.
This is really interesting work. One of my questions is, are you considering modeling sort of unusual supernova 1As, ones with circumstellar material or odd symmetries or things like that, to see if you can identify these systems readily in the data?
That's a good question. Do we have those in The Sims? Like, especially unusual ones?
We have some unusual ones. I believe Ben might be in the best place to answer this,
Yeah.
Ben Rose. I can bring you a mic.
I know we have, ones that aren't. We have like 1AX, but I don't know if we have like the super weirdos,
Yeah, that's where I was leaning. Do we have, I guess we would need some templates for the early and late phase of those specific ones, but looks like Michael has an answer.
The transients that exist in there span the range of point source variability on extended sources from which you could reconstruct, right, any particular light curve. So, I mean, a lot of this is testing the, do we recover from pixels the flux that we put in for things that go up and down, and we understand how we do photometry with different flux versus background surface brightness things. So from that, going to a catalog is the key thing. If you had different things that had different properties, I think that mapping still allows you to answer that same question in principle. You don't have to simulate everything all the way to the pixels. I think what we're simulating spans the space of things that you would be deeply interested in.
Any additional questions? If not, then I will do a shameless plug, because there is a Supernova Pit hack session this evening if you'd like to join and bring up things like this. I believe it's at 4 p.m., so please feel free to join. Otherwise, please let's thank our speaker. Thank you very much.